Hi, everyone. So then I have now discussed a subspace and its orthogonal complement. These are two subspaces that they both sit inside Rn. We know that they don't really intersect other than the zero vector. So then we'd like to know how these two subspaces somehow break up or decompose the overall space Rn. That leads into the idea of projections and also, possibly more importantly, the really neat orthogonal decomposition theorem. So I'm going to give you an idea of how to do this with numbers first. Then I'll mention the theorem. And then if you want to stick around for the proof, you can. There's nothing after that, though. So first, with just an easy example that you can actually see. Suppose you have a plane. Now I want to find, what do I mean by the projection of a vector that's not in the plane upon that plane? That would be the projection of the vector upon the plane right there. And then this is the component of V that's going to be orthogonal to that plane. These two vectors have to be orthogonal to each other, so their dot product must be zero. And when you add them together, you must get the vector V. So the question is that, well, how do you find the projection? Once you find the projection, finding this other vector is not difficult. It'd be just the vector V minus the projection. So let's assume for a minute that the plane has an orthogonal basis, U1 and U2. What I'll do is I'll take the vector V and I'll project that vector V upon U1 and upon U2. I claim the projection, as hinted at by this picture, the projection of V upon the plane is actually found by just taking the projection of V upon U1, the projection of V upon U2, and then just adding those projections. So I'll give you a numerical reason, a numerical computation first to kind of support the result. Let's see if that idea is right first. Let's say the vector is 1, 2, 3. The two vectors that are going to be making my plane are going to be U1 and U2, as you see here on the screen. And I want to find the projection of the vector V upon the plane that is spanned by U1 and U2. So to do that, it's just projecting V upon U1, projecting V upon U2, and then just adding those projections. That's the result. So that should be the projection, if we're right. To find the component of V that's orthogonal to the plane, we just take V minus this projection. So that would then be that other portion. Now, if these are correct, then if I add them, I get V. If I take their dot product, I get 0. And in fact, that's exactly what happens. So that looks good. There's a concern you might have, though. Now, the theorem that I'm about to give you also implies that the projection is independent of basis, which means it doesn't matter how you represent the plane. Any orthogonal basis will work just fine. You'll always get the same projection because there is only one projection. So just recall moments ago, I gave you the vector 1, 2, 3. That vector is definitely not in the plane described by x plus y plus z equals 0. And that plane just happens to be the span of the two vectors I gave before. So I've already done the projection. I've done it once. That projection is -1, 0, 1. But you can use a different orthogonal basis. This set of vectors, 1, 2, -3, -5, 4, and 1, both satisfy the equations of x plus y plus z equals 0. So those two vectors lie in the plane. And those two vectors are orthogonal to each other. So they are just fine as an orthogonal basis for this particular plane. So if we once again go through the process of finding the projection of V upon this plane, I would take V and I would take its dot product with this vector. And then I'll take the projection of V upon this vector. And I would take the projection of V upon that vector. That's these two things. And now I add them up. And when you do add them up, you get the same answer. You still get the same projection. And the reason is because there's only one projection when you project a vector upon a space. It doesn't matter if it's a plane or not. So it's independent of the choice of orthogonal basis you pick for that space. And that's really pretty nice. So just the theorem first. If you give me any subspace of Rn, then every single vector in Rn there are two vectors, one in the subspace and one in its orthogonal complement. So the vector v is the sum of the two vectors that are guaranteed. Moreover, that vector w that's in the subspace w has got to be the sum of the projections of v upon the different vectors in the orthogonal basis for the subspace w. So then, since this theorem says there's only one such vector in w and only one such vector in w perk, we can give them names. So we'll call them the orthogonal projection of the vector v upon the subspace. So if you give me a subspace and an orthogonal basis for that subspace, every vector in Rn, we can then define the orthogonal projection of v upon w, written as we've been writing it. And it is then just the sum of the projections of v upon the orthogonal basis of the subspace. And then you just add those different projections together. And the component of v that's orthogonal to the space, which is written here, as I've written here for you, is just the vector, which is the vector v minus the projection. So then that's the theorem. If you want to stop here, you've already seen me use the result twice. So then you can do projections on your own now. The second half of the video is about proving this result. It needs about 3 slides worth of work. It's not difficult, but it does require a little bit of work. So you can stop here if you want. All right, so assuming then that you are here for the long haul, let's go talk about it. So suppose you have v is any vector in Rn, say u1 through uk is any orthogonal basis for w, that subspace. Define the projection of v upon the subspace as the sum of the projections of v upon the different basis vectors in the orthogonal basis, and define the component of v orthogonal to the space to be the difference between the vector and that projection. I have to then prove to you lots of stuff. First, I'm going to convince you that this projection is actually in the space. It's actually in W. So then why? Well, notice that the projection of V upon any of these vectors, U1, U2, so on, is just a multiple of that vector. It's a multiple of that basis vector because projections are a scalar times the vector. It's in the direction of the vector. It's just, I don't know the length. So that means that by definition, the projection of V upon W is a linear combination of the vectors U1 through UK. It is therefore in W by definition because W is the span of those things. Next, I gotta convince you now that the component of V orthogonal to W actually is orthogonal to W. So I have to prove to you then that if you take this particular vector and take its dot product with anything in W, it's 0. Well, to do that, all I have to do, from a thing we said about orthogonal complements, I have to just convince you that the dot product of this vector, which I'll call perp V from now on, its dot product with any of the basis vectors for W is 0. So doing that's not difficult. It's a matter of just smashing out the notation. So here is the dot product. We know what perp V is. It's the vector V minus the projection of V upon W. But we know that projection is by definition, it's a sum of projections. So then that subtraction becomes a long list of subtractions of vectors. Notice I isolated one of them. That's the projection of V upon UI. The reason is that this thing here is some multiple of U1. This guy back here is some multiple. I don't know what that multiple is. It's some multiple of UK. So if I take the dot product of UI with that one, since the subscripts of UI and U1 have to be different, that's why I isolated this guy right here. That's got to be 0. So I don't have to worry about that dot product. And the dot product of UI with UK is also 0. So I don't have to worry about that dot product. In fact, a whole lot of these dot products don't matter. The only one that does is the dot product of UI with V and the dot product of UI with the projection of V upon UI. So we have that now to worry about. But we know a formula. We know the formula for the projection of V upon UI. It's just that. But notice then that you have UI dotted with itself, both being multiplied and being divided. So they cancel, giving you then V dotted with UI minus the exact same thing, that's 0. So then the perp of V is therefore orthogonal to every single basis vector that defines W. It is therefore, of course, orthogonal to all of W. And that's why I have the show. Cool. That then shows that these two vectors are in the right spaces. So then the orthogonal projection of V upon W actually is in W, and the component of V orthogonal to W actually is in W perp, orthogonal to W. Now, the really interesting one, I have to show you that it's unique. I have to prove to you that if ever you have a vector V and it's written as a sum of a vector in W and a vector in W perp, that thing is going to be unique. There's only one way to do that. So let's pretend there's two. So then let's suppose that V can be written as a sum of two vectors, one in W, one in W perp. And then it can be written another way, one in W and one in W perp. I'm going to convince you that A has to equal B and A perp has to equal B perp. It's not difficult to do. It's just a matter of, again, messing with notation. So notice then this equation means that A minus B has to equal B perp minus A perp. But notice that these things are subspaces. So A minus B are both in W. So that difference then is also in W. B perp minus A perp is in W perp, but that's a subspace. So their difference is in the same subspace. But these things are equal. That implies then that A minus B is in W and A minus B is in W perp. So it's in their intersection. Well, but there's only one vector. There's only one vector in the intersection of a subspace and its orthogonal complement. That's the 0 vector. So A minus B has got to equal 0. But that means then A has to equal B and that A perp equals B perp, which means that this representation is unique. If you ever have a vector V, it can only be written one way as a vector in a subspace plus a vector in its orthogonal complement. That's a really neat result. That is, by the way, the reason why when we have that mapping of a matrix that's M by N, that goes from Rn into Rm, that the row space and the null space being orthogonal complements, every vector in Rn can be written uniquely as a vector in the row space plus a vector in the null space. And which is that diagram I gave you, it actually is true. It's actually kind of true. Okay, good. That's enough for this video. I believe you have gotten through this. If you watched the proof, good job by you. This is not an easy one to follow along because there's so many symbols, but the idea is very easy. It's just difficult to get there.